And the next one is discriminative functions. Okay, so as I said, we don't have to model probabilities exactly. So as long as we can classify, then that's enough. So we want to make one function g of x, and we can use some sub-functions g sub 1 and g sub 2 and g sub c, and then we can use something like a maximum, then g of x. So for example, if g of 1 is p of w1 given x, okay, and this one is w2 given x, wc given x, then if we use a maximum max operator, then this is this one decision function based on this posterior. Or we can use some likelihood. Instead of these ones, we can use likelihood. Or we can use base risk. Okay. And so on. So based on these functions, then based on this max operator, then we can define one decision functions. Or in machine learning algorithms, we have many different decision functions, not just based on these probabilities. Okay, so we can find this decision function directly. Okay, and we can replace g of x by f of g of x when f is monotonically increasing function. Okay. Now let's talk about the decision boundary in detail. And for two-class problem, when we have sub-functions like g sub 1 and g sub 2, and depending on the evaluation, then we can classify x into class 1 or class 2. So if this one is higher than larger than this one, then it is class 1, otherwise class 2. What about the boundary? How about this one? In this equation, it says class 2, but it's up to you. So we want to find this boundary like this. And instead of comparing this one, if we define g of x in this way, then if g of x is positive, then it's class 1, otherwise class 2. Basically the same thing. And for minimum error rate case, we just check this one. Okay, we compare the probability of class 1 given x and probability of class 2 given x. So if it is positive, then class 1, otherwise class 2. So in this case, g sub I is actually p of omega I given x. And with the base rule, we can derive this equation. So this one becomes this one. This one becomes this one. Actually, p of omega 1 given x is p of x omega 1, p of omega 1, p of x. But as I said, regardless of these classes, p of x is kind of constant. When the x is given, this one is constant. So we don't care this one. So as long as we are actually comparing this one, then we can focus on this one. So we just focus these ones. And then we take a log, because log is a monotonically increasing function, so it doesn't matter. So we apply a log function. Then we can rearrange this term. This one goes here and this one goes here. So we have two terms. And this part is independent of x. This one is about the prior. So if we have no idea about the prior information, then we can ignore this. Okay. If p of w1 is higher than p of 2, if we know that kind of information before looking at the data sample, then we can use this term. But anyway, this term is constant. It has nothing to do with x. So we can focus on this one. Okay, now in the previous slide, we just used p of x given omega 1 or p of omega 1 given x in general form. So p could be any probability distribution. But from this slide on, we want to focus on Gaussian distribution because Gaussian distribution is simpler than any other distributions. And if we will use a g sub I of x for Gaussian, then this one is a g sub I of x. Instead of g sub I, we can use this one, and this one is a still general notation, but instead of this one, we can use this. Okay, given this class, then we have this mean and variance. Again, in this chapter, we assume that these parameters are already estimated. So we have these parameters. So we can actually use Gaussian distribution for this one. And in this case, this one is not a Gaussian. But as we saw in the previous slide, this one can be replaced by this one. Okay, so we have a log term here. Then if we apply log to Gaussian distribution, then we have a quadratic equation here, and this one is a constant, and if this one is fixed, then this one is constant and this one is constant. But when we have two classes, then sigma 1 and sigma 2 might be different. Then we cannot ignore this part, even though this one is fixed. But anyway, here we have a quadratic equation. So as long as it is quadratic, then we can solve the equation. Okay, this one is a g sub I. Okay, and when we handle Gaussian distribution, there are a couple of different cases. Okay, first one, when the features are uncorrelated, which means independent. When it is a Gaussian distribution, when the features are uncorrelated, which means Gaussian distributions are independent with the same variance. Okay, independent, and we assume that they have the same variance. Then Gaussian distribution can be represented by sigma squared times I. So basically, this part means features are uncorrelated and independent. And same variance means this one. So we have the same variance for all the diagonal elements. And then this one is actually sigma squared times I. Then this equation becomes simpler. So the determinant of this sigma I is variance to the power of d. And inverse is quite simple too. Okay. So g sub I of x is simply this one. And this one is constant. So this part is constant because it is independent of class. Okay, so ignore this part. Then we have this term for this one, and this one is also constant, so we can ignore that too. And this one, so this one can be rewritten by this one, and we have this term. Okay, this one is a g sub I of x. From the previous slide, we got this. G sub I of x is like this. Okay, now we want to delete more kind of constant terms and some terms that are independent of classes. Okay, this part can be rewritten in this way. And x transpose x is independent of class I. So we have class I here and here. So this term can be deleted from g sub I. Okay, so what we are doing here is that we want to delete all the terms that are independent of class. So these terms have nothing to do with classification. Okay, so we just delete this term. Then now g sub I looks like this. And if you look at this equation carefully, then this one is linear equation. So this one is w sub I, and this one is w sub I(O). Then now this one is a linear equation. G sub I is a linear equation. Good. Okay, then let's check this decision function g of x, which is g sub I minus g sub j. And when g of x is 0, then we can find one curve. Then that is the boundary curve. Okay, And when this one is 0, then from this equation, this one is g sub I is wi transpose x minus woi. If we use this term, then g sub I is here and g sub j is here. Okay, now if we define w in this way and x naught this way, then this equation becomes this one, which means w should be orthogonal to x minus x naught. Okay, now let's see where the boundary is. Okay, so we put this into 0. Then the solution of x, which means the boundary. The decision surface is actually a solution of x such that this x minus x naught should be orthogonal to w, where w is this one and x naught is this one. Then let's take a look at this figure on the left side. And this one is mu I and this one is mu j. And mu I minus mu j, this one is w. And x minus x naught should be orthogonal to this line. So something like this blue line. Then where is x naught? So x naught is average of these two mean and plus k times ui minus uj. So this one, this vector is this term. And u sub I minus u sub j is this vector. Okay. And we have a scale k. So depending on k, this could be this one or it could be negative 1. So this blue dotted line is moving from here, and if k is small, then it could be this. It could be this, depending on the value k. So which means when we have a two Gaussian distribution like this one and this one, if they have the same kind of prior distribution, then we have the decision boundary right in the middle of these two distributions. But depending on this k, okay, then this boundary could be here or here. Then let's talk about the effect of prior. In the previous slide, the k was defined in this way. Let's go to here. Okay, k is this one. And if probability of omega I is larger than greater than p of omega j, okay, this one is greater than this one, then this one is positive, then negative. So finally k is negative, which means x naught will move close to uj. If k is negative, this one, something like this line. If wi is smaller than this one, then this one will be negative, and with this minus, total k will be positive. Then we will have the boundary around here. So what does that mean actually? Okay, look at this one. If p of wi is greater than p of wj, which means we have a higher prior than for wi than wj, omega j, sorry. Which means we prefer class I than class j. So boundary is moving from here to here, which means if x is around here, then we will classify this one into class j. So if we have a preference to this class, then we move this boundary toward this class, something like this one. If we have a preference to this class, then the boundary will be like this. So what we're doing here is that when we have a two Gaussian distributions, when the covariance matrix is identity matrix with same variance, sigma square, then the contours are just the circles, okay? And then depending on the prior, we have a linear boundary, okay? Okay, we have another case. In this case, the classes have identical covariance matrices. So this sigma could have some arbitrary numbers, something like 0.2, 0.7, 1.2, 2.1, something like this one. Okay, so this is not diagonal matrix. This one is just a normal matrix with arbitrary numbers, but we have the same covariance matrices for class 1 and class 2. So for G sub I, instead of sigma I, we can have just the sigma. So this one is independent of class, okay? But we might have different mean, mu I, and different prior. In this case, boundary surface such that Gi minus Gj is 0 is a linear. So this one is a linear. If you have more time, then you can calculate the equations by yourself. Okay, we are not going to go further than this. Okay, this is enough, I guess. And for case 3, when each class has a different covariance matrix, it's just general case. Okay, each class has its own covariance matrix, and this one is a matrix of arbitrary numbers, 0.5, 1.2, 2.3, 0.7 kind of things, for example. And sigma j is another matrix, 7.2, 2. Something like this. So it's just a general case. Okay. Then we have mu I here and sigma I here and mu I here. So we cannot delete any terms with the mean and variance. So in this case, if we find the surface such that G sub x is 0, it could be something like this. This one is in the two-dimensional space. This one is in the one-dimensional space. In the one-dimensional space, for this region, it belongs to class 1 if the blue one is class 1. And for this one, class 2 and class 2. Or we might have this kind of case. Okay, the boundary is here. Okay, so in the one-dimensional space, we have one boundary, and for this region, the model says the x is classified into class 1, and for this one, class 2. Okay, this is it. In this chapter, we talked about decision theory. And in decision theory, we talked about 3 different approaches. First one is a generative model, and the second one is a discriminative model, and the third one is a discrimination function. Okay, and for first 2 approaches, we talked about the probability distributions. Okay, and for the third one, we started with probability distributions, but at the end, we actually use just the functions. Okay, so we don't care the probability anymore. As long as it can classify, then it's enough.